Hello students. In our previous lecture we discussed about the superposition principle, where we discussed about the combined effect of waves successfully, that what is the net displacement psi at a point in space where waves with independent displacement psi 1 and psi 2 exist together. So in today's lecture we are going to discuss the superposition of waves which have the same frequency. Clear? If two or more waves of the same frequency arrive at a point P in space, so what will be the effect of the resultant wave at that point? So for instance, let us consider two optical waves which have the same frequency but they are differ in amplitude and phase. Here this is the first wave which is traveling in this direction, having amplitude E1, and it covers a distance S1 and reaches this point. Here this is the first reference plane for the first wave, and here this is the second wave which is traveling in this direction and it covers distance S2 and then it reaches this point P. This wave has an amplitude E2 and this is its initial reference plane. So we take the waveforms of these two waves as, let's suppose E1 is written as E0 1 into cos of k S1 minus omega t plus phi 1. That this is equation number 1. And for the second wave, which is E2, is equal to E0 2 cos of k S2 minus omega t plus phi 2. That this is equation number 2. Here E0 1 and E0 2 are the amplitude of the first and second wave respectively, where we told that both the waves have the same frequencies. So here both the waves, I have written both the waves in the form of their wave number. S1 is the distance traveled by the first wave from its reference plane to the point of superposition, and S2 is the distance traveled by the second wave to the point of superposition. And phi 1 and phi 2 are their initial phases of the individual waves at time t equals to 0. Clear? To simplify the notation, let we introduce constant phases to simplify the notations. We introduce constant phases. Such as alpha 1, let this k S1 minus plus phi 1, this is alpha 1, and for k S2 plus phi 2, this is alpha 2. Let this is equation number 3, and this one is 4. Thus the time variation of the electromagnetic waves at a given point thus can be expressed as E1 will become equal to E0 1 cos of alpha 1 minus omega t, and for E2 this will become equal to E naught 2 cos of alpha 2 minus omega t. Clear? This is equation number 5, and this one is 6. So these two waves which are intersecting each other at point P, they only differ by phase. These two waves only differs in phases, and their phase difference is alpha 2 minus alpha 1. This is the phase difference between the two waves, which is simply k s2 minus s1 plus phi 2 minus phi 1. This is the phase difference between the two waves. Here the first term is due to this phase difference is due to the path difference between the two waves, and the second term, this is phi 2 minus phi 1, is due to the initial phase difference of both the waves. So if two such waves superpose each other at some space, clear? So the resultant wave will be of the form which is ER is equal to E1 plus E2, and this will be equal to E naught 1 cos of alpha 1 minus omega t plus E naught 2 cos of alpha 2 minus omega t. This is equation number 7. So if two waves, if they superpose each other at some point of space, and the resultant wave will have three forms. The nature of the superposition at a fixed point in space of two harmonic waves of the same frequency are going to be discussed, and it will have three forms. Either we will have constructive interference, Clear? So consider this figure. Here we have two waves of the same frequency. Here the amplitude of this wave is E1 and the amplitude of this wave is E2. These two waves which have the same frequency, but they are slightly different in amplitude. So in this situation you can see that their initial points occurs at the same time, and after going in forward direction they are in step. Here we can see that at the same time their crests occur, or the peak points occurs, and also at the same time their troughs occurs. So here in this case their amplitudes are just simply added. The amplitude of the resultant wave, which is ER, is equal to E01 plus E02. Their amplitudes are just added. Clear? So if two waves of the same frequency are in step, that means that their peak points occurs at the same time. So the resultant wave, then the resultant wave will be, the amplitude of the resultant wave will be simply the sum of the two waves. Clear? So here two waves which are given by equation number 5 and 6, they will only interfere constructively if their phase difference, if this value alpha 2 minus alpha 1 is integral multiple of 2 pi. Equation 5, the waves in equation 5 and 6 will only interfere constructively if their phase difference, that is alpha 2 minus alpha 1, is equal to m times 2 pi, where m is an integer. Clear? Where m is an integer. That means that is the resultant wave will be equal to E1 plus E2, which is E01 into cos of alpha 1 minus omega t plus E02 into cos of alpha 1 plus 2m phi minus omega t. I have told you that if the phase difference between the two waves is integral multiple of 2 phi, that is, if alpha 2 minus alpha 1 is equal to 2m phi, then alpha 2 will be equal to alpha 1 plus 2m phi. So I have just substituted alpha 2 as alpha 1 plus 2m phi. So this will be now equal to E01 plus E02. As you can see that their amplitudes are simply added into cos of alpha 1 minus omega t. Clear? And in the diagram it is shown here in this figure. Here this wave has an amplitude of about 1 and this wave has an amplitude of about 0.5. As you can see that they are exactly in step, So the amplitude of the resultant wave is simply their sum, which is 1.5. Clear? And the resultant wave has exactly the same frequency as the individual wave. Now another case, which is destructive interference. Destructive interference. If the two waves which have the same frequency but they are out of phase, that means that they are out of step, such that their peaks doesn't coincide, or we can say that if the peak of one wave exactly occurs with the trough of the second wave, and similarly the trough of the first wave with the peak of the second wave, as shown in this figure. You can see that here in the figure, two waves which have the same frequency and same amplitude. The amplitude of the two waves are about 1. Clear? Which is from here to here, this is 1, and for the second wave this is also 1. So here we have two waves which have the same frequency, same amplitude, and they are arriving at the same point in space at a given time, but they are out of step by 5 radians. The phase difference between them is 5. Clear? So they cancel their effect and the resultant wave is vanished. Clear? So destructive interference will occur if two waves of same frequency but having phase difference of odd integral multiple of phi. If two waves which have the same frequency but they are out of phase by amount of odd integral multiple, so they will destructively interfere and they will cancel the effect of each other. That means that if alpha 2 minus alpha 1 is equal to 2m plus 1 times phi, where m can be any integer which is 0, 1, 2 and so on. Clear? In this case, if you substitute alpha 2 equal to this value, which is alpha 1 plus 2m plus 1 times phi in the equation number for this value here, alpha 2, so the resultant wave will be of the form E1 plus E2, and this will be equal to E01 into cos alpha 1 minus omega t plus E0 2 into cos. For alpha 2 I have to write alpha 1 plus 2m plus 1 times phi minus omega t. So this will be equal to E naught 1 minus E naught 2. As you can see that in constructive interference both the amplitudes were added, and in destructive interference both the amplitudes are subtracted from each other into cos of alpha 1 minus omega t. Clear? So also note that if both the waves have the same amplitude, if E naught 1 and E naught 2 are equal, then the resultant wave will vanish. Clear? Now if the two waves which are neither in step or out of step, so we have to generalize the case, which is general superposition. Now we are going to discuss if two waves which have the same frequency but neither they are in step nor out of step, and we have to discuss their superposition. The general case of the superposition of two waves that are neither in step nor out of step is also given in this figure. You can see that here these two waves which have exactly the same amplitude, same frequency, but they are neither in step nor out of step. Clear? As you can see that at time t equals to 0, the amplitude of this wave is 0. This wave is at the 0 point, while this wave has amplitude of about 0.5. Clear? And if they superpose each other, the resultant wave is between the amplitude of the resultant wave is between E naught 1 plus E naught 2 and E naught 1 minus E naught 2. If two waves of the same frequency, same amplitude, they are neither in step nor out of step, and they superpose each other, then the amplitude of the resultant wave will be between E naught 1 plus E naught 2 and E naught 1 minus E naught 2. That means that their amplitude will be between the amplitude of their sum and the amplitude of their difference. Clear? So that is the intermediate value of the amplitude. So if two waves of same frequency which are neither in step nor out of step, so for this general case, the resultant field, which we usually describe by this equation 7, of equation 7 can be simplified by writing the fields in complex form. And by using phasor diagram. Clear? So consider, so we have to note that in the phasor diagram the amplitude of the wave is given by the length of the vector, and the phase of the wave is given by the angle of the vector with the horizontal axis. So let me explain it here in this figure that we have. This coordinates, this is the horizontal axis and this one is the vertical axis, and this wave, which has amplitude E01 and it has a phase alpha 1. Clear? And the second wave, let me write here, the second wave which has amplitude E02 and it has an angle alpha 2, which is its phase. I have told you that in the let me write, this is the reference plane, and let so this wave has some phase, this is, and that phase is given by the alpha 1. Clear? And it has an amplitude E01. Clear? So in the phasor diagram, the phase, which is this value, this is given by alpha 1. Clear? It may be either 70 degree, or it may be 0 degree, or it may be whatever any value. Clear? So the phase of the first wave, which is alpha 1, and this is given by the angle of the vector with the horizontal axis, and the amplitude of the wave is given by the length of the vector. Clear? And the second wave, which has greater amplitude and have large phase angle. Clear? Which is of the type of, or the form of this one. Clear? So this one has amplitude E naught 2, and for this one it has amplitude E naught 1. So if we are going to add these two waves, so we have to add them according to vectorially. I can place the second vector, the tail of the second vector, and the head of the first vector. This is E naught 1, and it has a phase alpha 1. And if I put the tail of the second vector, which has amplitude E2, and it has phase angle alpha 2, then the resultant wave will have amplitude of about this one. Clear? This has the amplitude ER. This is the resultant wave, and it has a phase angle of this one, which is about alpha. Clear? So therefore the resultant wave will be equal to to find ER1, which will be E naught 1, or simply, sorry, not E1, E naught 1. It has, this is E1 plus E2. Clear? Note that we have to add them according to vectorially. That means that in physics we treat complex quantities as vectors. The magnitude of the vector or the length of the vector gives the amplitude of the wave or the magnitude of the complex quantity, and the direction of the vector gives the phase of the complex quantity. Clear? So in order to add them, we have to first resolve them into their components. If I resolve this vector E1, so it will have two components. This one will be E naught 1 from here. If I resolve this vector E naught 1 into two components, so one will be from here to here, from this point to this one, it will be E naught 1 cos alpha 1. Clear? And this one will be from here to here, this will be E naught 1 sin alpha 1. Clear? And similarly, if we resolve this E2, it will have two components, which will be from here to almost here, and it will have the value E naught 2 cos alpha 2, and this will be E naught 2 sin alpha 2. Clear? So the two components of the resultant wave will be, which will be E naught cos alpha. If we add E naught 1 cos alpha 1 plus E naught 2 cos alpha 2, this will be equal to E naught cos alpha. it will be E naught 1 cos alpha 1 plus E naught 2 cos alpha 2. And similarly for the vertical component of the resultant field, it will be E naught sine alpha, which will be equal to E naught 1 sine alpha 1 plus E naught 2 sine alpha 2. Clear? Remember, here the horizontal component gives the one component of the resultant field, and the vertical component, which is E naught sine alpha, gives the second component of the resultant field. Also, in complex quantities, the horizontal values or horizontal line gives the real part of the complex quantity, and the vertical line represents the imaginary part of the complex quantity. So therefore the magnitude of the resultant wave will be simply can be found by Pythagoras theorem, which is E naught square is equal to E naught 1 square plus E naught 2 square plus 2 E naught 1 into E naught 2 cos of alpha 2 minus alpha 1. This will be the magnitude of the resultant wave. This is equation number 8. Clear? This is easy. Let me write it as ER, because the resultant wave is ER. Square of this side is equal to the square of this side plus this side, so it will be E naught 1 cos alpha 1 plus E naught 2 cos alpha 2 whole square plus E naught 1 sin alpha 1 plus E naught 2 sin alpha 2 whole square. Clear? So by simplifying it, we will get this equation. So this equation 8 gives us the magnitude or the amplitude of the resultant field, and for the phase or the direction of the resultant field, we can write as the phase of resultant field is can be written as tan alpha, which is equal to this value divided by this value, which is E naught 1 sin alpha 1 plus E naught 2 sin alpha 2 divided by E naught 1 cos alpha 1 plus E naught 2 cos alpha 2. This is equation number 10. Clear? So in summary, we have shown that the two waves which are has the first wave is E naught 1 cos alpha 1 minus omega t, and the second wave was E naught 2 into cos alpha 2 minus omega t. So if these two waves, which are neither in step nor out of step, and they superpose each other, then their resultant field will have amplitude, which is given by this equation number 8, and that wave will have phase angle, which is given by this equation number 9. Clear? So I think this is sufficient. Also, it must be noted that if more waves, more than two waves, which arrives at a point in space and which have the same frequency but they are differ in phase, and we want to find the resultant field at that point, then we have to treat them as complex quantities, and we have to arrange all the waves according to vectorially. Let's suppose then we have to draw them, which is, let's suppose this one has amplitude E naught 1 and has an angle alpha 1 r phase alpha 1, and the second wave, which is E naught 2 and has phase alpha 2, and then the third wave, which has their own phase and amplitude, and so on. Clear? So the resultant field will be obtained using vector nature of the complex quantities. The amplitude of the resultant wave will be to find the length of this vector, and the phase of that resultant field will be the angle of this resultant field with the horizontal axis. So thank you very much.